Dense arrays of rigid scales embedded in soft skin protect animals from predator teeth. These natural armors have inspired many applications, including protective gear, soft robotics skins, and 3D printed fashion. To unlock the full potential of these scaled sheet materials, however, we must understand how scale shape and arrangement control macromechanical behavior. In this work, we present a computational approach for modeling the mechanical behavior of flexible scaled sheet materials, 3D printed hard scales embedded in a soft substrate. The curvature response of scaled sheet materials is highly complex. While they show little resistance to bending for small curvatures, larger curvatures induce contact between scales, which rapidly increases bending stiffness. Moreover, their asymmetric structure in the thickness direction leads to distinct bending responses for positive and negative curvatures. Each of these effects depends in non-trivial ways on scale shape and arrangement, making it challenging to predict the mechanical properties of a given pattern. To address this problem, we propose a computational approach for modeling the mechanical behavior of scaled sheet materials. The basis for our method is formed by an accurate native-level simulation model that combines soft-shell elements with hard volumetric scales and penalty-based contact. To probe the mechanical behavior of arbitrary patterns in simulation, we develop a uniaxial bending test with tailored periodic boundary conditions that generate desired curvatures without hampering in plane deformations. We use these data to construct a novel homogenized energy model that combines biquadratic uniaxial fits with polar interpolation based on circular harmonics. We show that this homogenized energy can be combined with standard discrete shell models to enable efficient simulation of large-scale patterns. In the first test, we use disc-shaped samples of 10 cm radius mounted onto a mandrel rotating at a constant angular velocity of 4.5 degrees per second. A simple force probe is used to impose constant displacement at the boundary of the sample. Readings from the force sensor are recorded continuously as the mandrel rotates, leading to a quasi-continuous force displacement plot. We used our method to characterize a representative set of patterns and observed a wide range of complex behaviors as shown in these moment curvature profiles. In particular, we observe highly direction-dependent stiffness and strong nonlinearities due to contact between scales. To validate the results obtained through native-level simulations, we performed experimental measurements on physical prototypes. As can be seen from these plots, we generally obtain good qualitative agreement between measurements and simulations. As another characteristic effect of scaled sheet materials, we furthermore evaluated the asymmetric stiffness of scaled sheet materials for positive and negative curvatures. For better clarity, we refer to curvatures as opening or closing to indicate an increase or decrease of the gaps between scales, respectively. In this example, the stiffness for opening curvatures is very low and stays roughly constant. The behavior is initially similar for closing curvatures, but once scales start to make contact, a significant stiffening is observed. Our native-level simulation faithfully reproduces this effect both at the scale level and macroscopically. Opening curvatures can likewise lead to contact. In this example, an arrow-like pattern is bent to produce opening curvatures, which leads to contact between scales and a corresponding stiffening. This effect is explained by the concave shape of the scales, allowing them to interlock and resist opening curvatures. Finally, we evaluate the accuracy of our macromechanical model relative to the native-level simulations by comparing moment curvature profiles for different patterns. As can be seen in this comparison, the macroscale model achieves overall good agreement with the reference data at a fraction of the computation time. Thank you for watching.